Dear students, in the previous class we learned that crystal field theory, and here we are ready to understand what type of complexes, how they are exhibiting the color, and how to understand the magnetic properties of these complexes. So here what we learned is these are the d orbitals. These are the d orbitals which are present, and their energy is increased. Then afterwards they are split into categories, mainly two categories, T2G and EG category. Now in such a case there is an energy difference between this one. If it is an octahedral splitting, the energy difference between these two is delta naught. In such a case, if these orbitals are having a vacancy like this, these orbitals are having vacancy like this one, what can happen? An electron can promote from lower set of orbital to another set of orbital by absorbing a part of visible radiation. As it absorbs a part of visible radiation, then what it will do means it will show complementary color. What we are naming this one as DDay transition, this one. So therefore, whenever a set of orbital is having vacancy, then the electron can promote from lower set of orbital to higher set of orbitals. Then what happens means they will be exhibiting color. And for this DDay transition, while the electron is promoting from lower set to higher set, what is happening means they absorb some visible radiation. As they are absorbing some visible radiation, complementary color is exhibited. So therefore, they are actually showing color. So complex compounds are showing color due to DDay transition. We will try to understand by taking an example of titanium hydrated complex TiH2O 6 times 3 plus. In this complex, titanium is plus 3 oxidation state and which is having single d electron, and this single d electron is present in T2G set and EG set is vacant. So therefore, by absorbing certain part of visible radiation, this d electron can excite from T2G set to EG set, and thereby what happens means it is showing color. Here the spectral analysis indicates that the absorbing color is blue green region and the complementary color whatever exhibited is violet in color. So therefore, by having this type of understanding, we can able to understand how the complexes are actually showing the color. By the same manner, what we can able to understand also, whenever we are able to write the configuration, appropriate configurations for the central metal ion present in the complex, then if there are any unpaired electrons, they are resembling what means paramagnetic nature, or they are responsible for paramagnetic nature, whereas there are no unpaired electrons, then that is resulting what means diamagnetic property also. So therefore, here we can able to understand color of the complexes as well as the magnetic behavior of the complexes by having the complexes and by understanding the splitting which is present between these sets of orbitals in the case of octahedral or tetrahedral like that. So therefore, it is very much useful to understand magnetic properties and color of the compounds. As the nature of the ligand it is changing, then the splitting energy also changes. Thereby the color also changes. For example, this is hexaaqua nickel ion complex which is treated with ethylene diamine. Whenever ethylene diamine is there, which is a strong field ligand, it replaces water. So the corresponding complex formed is NiH2O taken 4 times ethylene diamine, and it is pale blue color. Here In the first case, the nickel plus 2 is influenced by a weak field ligand H2O, whereas in the second case that is influenced by ethylene diamine. So therefore, the color it will be changing. As well as the same one what I am selecting the first one whatever product formed, it is again treated with one more ethylene diamine, 1 mole of ethylene diamine. Then 2 water molecules are replaced and it becomes ethylene diamine twice. So therefore, here again the influence of 2 ethylene diamine ligands are different from 1 ethylene diamine, and now the color is blue purple. So therefore, from this one what we can able to understand is, as the nature of ligand is changing, the influence of this ligand changes over the metal ion, and therefore it is influencing the energy difference between these two categories, that means two sets of d orbitals, thereby absorbed energy is different and corresponding complementary color also changes. So therefore, crystal field theory is useful to understand this color of the complexes. As we learned that or in the previous session what we discussed is, the main drawback is actually the crystal field theory is the bonding is ionic in nature, one of the difficult or limitations of crystal field theory. And second limitation here it is, according to this one, the negative charged one, because the splitting is due to between the ligands and the metal ion is due to interelectronic repulsions. So if I am selecting negative ions, they must show more actually influence, thereby the splitting must be more. But in spectrochemical series such as Cl minus, Br minus, OH minus, all these are acting as weak field ligands, and the neutral ligands such as NH3 or CO, they are having more splitting which is taking place by these ligands. So that was not explained by this theory, and this can be understood by the new type of theory or advanced one which is called as ligand field theory. Next, bonding in metal carbonyls, a very important bonding in metal carbonyls. Metal carbonyls are the complexes where the metal is associated with carbon monoxide, and such ones are called as metal carbonyls. Before going to discuss this metal carbonyls, I want to write what means the configuration of carbon monoxide in two ways. One is Lewis dot structure first. Carbon monoxide Lewis dot structure is this one, a triple bond is present between this carbon and oxygen, and this one is a lone pair is present over the carbon. So therefore, the carbon monoxide acts as a ligand. This carbon monoxide acts as a ligand by donating this lone pair of electrons. Whenever these metals are there, the metals are there and these are having vacant orbitals, what will happen means these vacant orbitals are accepting the electron pairs from this carbon monoxide. Thereby, the first bond formed between metal and carbon monoxide is the sigma bond. What bond is formed means sigma bond is formed. First, the metals which are having vacant orbitals, they are actually bonded by carbon monoxide with the help of a dative bond. Always the first bond formed is sigma bond. Now, if you come to the other one, now if you select this metal is having some d orbitals which are having what means the lone pair of electrons over the metal, the lone pair of electrons are also present. Say for example, I am selecting iron and the one iron carbonyl FeCO taken 5 times. Now, what is the central one is in this complex? Iron is the central metal, iron, whose oxidation state is 0. Therefore, what is the configuration here? It is argon 3d6 4s2. Argon 3d6 4s2. And if these these electrons which are present in d orbitals are get paired, then some vacant orbitals are available. That what we learned in crystal field theory. Whenever a ligand is approaching, then these orbitals are splitted. Thereby what happens means the arrangement of electrons takes place. Since we know that from the spectrochemical series, carbon monoxide is a strong field ligand, so therefore the d orbital electrons are actually paired up. In such a case, whenever these d orbital electrons are paired up, okay, some vacant orbitals are resulted. Into the vacant orbitals, the carbon monoxide is donating the electron pair, and the first bond formed between metal and carbon monoxide is a sigma bond. Now what is happening here? These d orbitals are having pair of electrons, some lone pairs are present over the metal atom also. These electrons which are present in these d orbitals are given back to the vacant molecular orbital which is present for carbon monoxide. There is a vacant molecular orbital. This is vacant molecular orbital, and into the vacant molecular orbital these d electrons are given back, and this is called as back bonding. What this is called as back bonding. So that the second bond is formed between metal and carbon as the pi bond. The second bond always formed is pi bond. So therefore, between metal and carbon monoxide, not simply a sigma bond is formed, and there here two bonds are formed, a sigma bond as well as pi bond is formed, and thereby what happens means the strength of the bond between metal and carbon monoxide is much more, and that becomes stronger. This effect what it is present and which is resulting stronger bond between metal and carbon monoxide is called as synergic effect. Synergic effect. The synergic effect is due to formation of both sigma bond and pi bond, and so therefore metal carbonyls are very stable. That's why in our blood also, whenever we are inhaling carbon monoxide, then the Fe+2 is strongly bonded with carbon monoxide because of this synergic effect, and it cannot be replaced by water or what means the oxygen molecules, and thereby the hemoglobin is losing its nature. And now in such a case, whenever a human being is exposed to atmosphere of carbon monoxide, loses the oxygen transporting capacity, so it leads for what means even death also. So therefore here what we are able to understand here is the carbon monoxide acts as a ligand, and it is forming a sigma bond first, then the remaining electrons present in the d orbitals of metal that will be given back to carbon monoxide into the vacant molecular orbital, forming a pi bond. And due to this formation of a pi bond, a double bond character is arised between metal and carbon monoxide, and the bond becomes very stronger, and this effect is called as synergic effect. And thereby what happens means these metal carbonyls are becoming very stable. The metal carbon bond which is a pi bond which is there, it is formed by the donation of electron pair from the filled d orbital of the metal, and the accepting orbital present in carbon monoxide is vacant anti-bonding of pi star molecular orbital. Pi star molecular orbital, very important. This one is the metal is giving the d orbital electrons, and the carbon monoxide is accepting the electrons from what means these metals into vacant anti-bonding pi star orbitals. Some examples for these metal carbonyls, whatever they are: nickel carbonyl, NiCO taken 4 times, where this carbon monoxide, it is tetrahedrally bounded around nickel. This one, it is tetrahedral, and so that we can say hybridization is sp3. Whereas in iron carbonyl, this one iron, it is surrounded by 5 carbon monoxides and FeCO taken 5 times, and the structure is triagonal bipyramidal. Triagonal 5, these carbon monoxides are present as triagonal bipyramidal. Whereas another one is chromium carbon monoxide complex, CrCO taken 6 times, which are octahedral. The coordination number is 6, so octahedral. And these are the special examples which are mentioned in our textbook, where there is a bond between metal and metal also, such as Mn2CO taken 10 times and CO cobalt complex, CO2 CO taken 8 times, and particularly here the CO acts as a bridged ligand. 2 carbon monoxides acts as bridged ligands also. And these are the certain examples which are there, and all these are stable, and therefore this type of stability is actually known as a synergic effect, and these are finding out what means some importance in metallurgy also. Just we will discuss this one in the what means next one, that means where we are going to applications of applications of coordinate compounds, there we will discuss. So this is about metal carbonyls. Let us find the applications of coordinate compounds in various regions. One is in the what means qualitative and quantitative analysis. Qualitative and quantitative analysis. In this case, we are generally using chelating ligands such as EDTA, ethylene diamine tetraacetate, DMG, dimethyl glyoxamate, alpha nitroso beta naphthol or cupron, etc. This type of chelating ligands, they play a very high role in the qualitative as well as quantitative analysis. For example, we know that hard water contains Ca plus 2. As that is containing Ca plus 2 and we are using EDTA, then the Ca plus 2 can be what means precipitated as the form of complex. Then what happens means how much of EDTA can be precipitating this Ca plus 2, thereby we can estimate the amount of the calcium ions present in the hard water. That what we are saying qualitative and quantitative ones. For example, a ore is there which contains nickel ore is present. Okay. Then if that ore contains nickel or not, first how to find out? We are using dimethyl glyoxamate 1. So the ore is dissolved in suitable solvent. Then for that one, what is added means dimethyl glyoxamate, DMG is added. And the DMG forms a very stable compound or complex with nickel ion. Thereby what happens means this one, it gives a particular deep blue color, so that we can understand that one ore contains nickel plus 2 ions. And then afterwards that one will be precipitated, as the precipitation is there, and we can estimate how much of nickel is also present in the given ore. So therefore, as the mineral, it is giving a color with DMG as well as it can be precipitated, then what can happen means we can estimate whether the mineral contains nickel ion as well as how much of nickel will be present in that mineral also we can be calculated. That means the qualitative and quantitative analysis, these formation of complex compounds are useful. So this is one use. As we are discussing, we can estimate what is the hardness present in the water, whether it is due to calcium ions or magnesium ions can also be estimated by using Na2-EDTA. EDTA acts as a chelating ligand. As it is combining with Ca plus 2 or it is combining with Mg plus 2, then the EDTA forms what means the chelating complexes with both of them, but their stabilities are different. By calculating the stability constants, we can recognize whether the hard water contains Ca plus 2 or the hard water contains Mg plus 2. So, therefore, we can able to recognize which type of ion, that means qualitatively we can able to understand. Next, by precipitating them as the stable complexes, we can estimate how much of calcium ion is present or magnesium ion is also present. That means quantitatively also we can estimate. Thereby we can recognize what means which method is suitable to what means remove these calcium ions or magnesium ions, that means hardness of the water. Another use of this complex compounds is in metallurgy. In metallurgy it is useful for the purification of ore and purification of the metals. For example, if we are selecting bauxite Al2O3, then it is leached with NaOH. Leaching means dissolving. Then the bauxite, it is dissolving in NaOH, giving rise what means a soluble complex AlOH taken 4 times, H2O taken 2 times, minus 1, a soluble complex, and the impurities are not dissolved. As the impurities are not dissolved, what happens means we can separate those ones insoluble impurities. Then afterwards by using suitable reagents, the aluminum can be regained as Al2O3. So, in metallurgy, similarly, in the case of what means the silver also, the silver say Ag2S is there, it is leached with what means the metals like this what means this one NaOH type. Then afterwards they are actually this one treated with high electropositive ones, and this can be leached with sodium cyanide actually. Then it gives first a soluble complex AgCN taken twice, AgCN taken twice. This soluble complex, whenever it is treated with high electropositive metal like zinc, then what happens means the silver will be extracted, leaving behind another complex what means zinc cyanide in the solution. So, therefore, what it is there means it is useful for the what means purification of ore as well as in the extraction of ore. Not only this one, in the same metallurgy, if nickel, impure nickel is there, it is combining with carbon monoxide, it gives what means nickel carbonyl. Nickel carbonyl. Whenever this is heated with carbon monoxide, then what happens means it gives a stable complex. Just only we actually learned that with carbon monoxide metals are forming stable complexes. So, therefore, a stable complex is formed. Okay. Then it is heated a very high temperature it is heated, then this complex is going to decompose to give back nickel and carbon monoxide. So, therefore, nickel will be purified. First, this is an impure nickel which is combining with carbon monoxide to give a carbonyl compound which is stable, but on strong heating this one is decomposed into nickel back, and which gives a stable what means or purified nickel, and that one it is used for purification of metals also. This particular process is called as Mond's process. These complex compounds are also finding various ways in biological systems also. They are actually present in biological systems also. For example, in chlorophyll, magnesium plus 2 is present where it is forming complex okay, and it is useful for the preparation of carbohydrates. Whereas, if I am selecting what means the cobalt ion that forms with in this one cobalt complex in vitamin B12, which is present as a complex, it is useful for overcoming the pernicious anemia. So, therefore, in biological systems also these coordinate compounds are finding some applications. Some other important uses of these ones of coordinate compounds are in catalysts, they are using as catalyst. Particularly in hydrogenation of alkenes, we are using Wilkinson catalyst, which is a rhodium complex. Its formula is PH3P taken thrice or HCl. Wilkinson catalyst is a coordinate compound which is used in hydrogenation of alkenes. Another one is another important application of this one is in photography. We are using photographic film where generally AGBR is present, which is exposed to light, but whenever undecomposed AGBR is there, it is treated with hypo Na2S2O3, where the silver it gives a soluble complex AgS2O3 taken twice 3 minus, and by that one the undecomposed AGBR can be removed, so that we will be actually making the photographic place to use. And another important use is in medicinal chemistry also. In medicines, as cisplatin is taken, PTNH3 taken twice and Cls, they are present on the same side. So, cisplatin it is used as anti-cancer, as well as EDTA is used to remove lead whenever the human beings are exposed for lead poison. Like that, if copper is there, then it can be removed by using D-penicillamine, and iron is removed by using desferroxime B, and like this so many applications are there for these complexes. By this one we are actually finishing these complex compounds. Thank you, students.